Good morning. VLSI stands for Very Large Scale Integration or Very Large Scale Integrated Circuit. What is the VLSI technology? What is the necessity of VLSI technology in our day-to-day life? If you observe that in our daily life we are using many electronic goods like mobile phones, smartphones, laptops, like that we are using almost all electronic goods and they are in smaller size. How it is possible to get this type of portable devices? Because of VLSI technology only. So what is an integrated circuit? It is a device which is consisting of more number of transistors on a small area. So that is nothing but a big circuit is constructed or designed on a small area, that is an IC. What is the necessity of these ICs? Before invention of transistors, we were using vacuum tubes. Those vacuum tubes are bigger in size and they are consuming more power and they are having less reliability. So due to that, scientists were developed transistors. Then these vacuum tubes are replaced by transistors, hence the size is reduced. So by depending upon number of transistors on an IC, they are categorized into small scale integration, medium scale integration, large scale integration and very large scale integration. So according to the Moore's law, the number of transistors on an IC will be doubled for every 18 months. This is called as Moore's law or Moore law. If you see here, this is our first computer, ENIAC. ENIAC stands for Electronic Numerical Integrator and Computer. It was developed in 1947. ENIAC was the first electronic general purpose computer. It can do simple arithmetic and logical operations. And if you observe the construction of this ENIAC, it is made up of with vacuum tubes, and this ENIAC is consisting of 20,000 vacuum tubes. So can you assume that what is the size of our first computer? The size of our first computer is around 1800 square feet. So that much area it is occupying. And it is made up of with vacuum tubes. Why? Because at that time no transistor was invented and around 7200 crystal diodes are used, 1500 relays, 70,000 resistors, 10,000 capacitors. So can you imagine what is the size of that our first computer? It is bigger in size and it is consuming 150 kilowatt of electricity. So it requires very huge amount of electricity. And due to these disadvantages, what are the disadvantages? Due to heavy number of components we are using in this ENIAC, it unable to move this in a computer from one place to other place. That is first disadvantage. And we are using vacuum tubes, they are consuming more power, they are larger in size, so they are having less reliability. So more failures are occurring in those vacuum tubes or other electronic components. So that's why more failures are occurring in the computer. Hence again you have to repair that. So these type of drawbacks are there and power consumption is very high. So what are the drawbacks? Area, it is occupying more area. Speed, it can do very small arithmetic and logical operations and the speed is very low. And power consumption is very high, it consumes more electricity. So these are the disadvantages. That's why transistor was invented. Then these vacuum tubes are replaced by transistors. Hence the size of this ENIAC is come down to our desktop, which is consisting of a CPU, a monitor and other peripherals which can easily place on any desk. Okay, so that is nothing but technology has developed. So these are the advantages of an IC. So after invention of transistor, again integrated circuits were developed which are consisting of more number of transistors on a small area. So due to that the size is reduced, speed is increased and they are smaller in size, hence power consumption is also low. So these three are advantages of integrated circuits: area, speed and power consumption. These are the three advantages of integrated circuits. So that's why after invention of integrated circuits we are getting this type of portable devices. By depending upon the density of transistors on an IC, these ICs are classified into SSI, MSI, LSI, VLSI. Small scale integrated circuits which are consisting of up to hundreds of transistors. Medium scale integrated circuits which are consisting of up to some 1000 transistors. Large scale integrated circuits which are consisting of up to some 10,000 transistors. And now VLSI technology, on which the number of transistors are increased to million. So how these ICs are fabricated? These ICs are fabricated by using either bipolar technology or MOSFET technologies. So bipolar technology is nothing but using TTL, ECL, okay, like that. But the drawback of bipolar technology is they consume high power. High power dissipation is there in bipolar transistors. And bipolar technology is used for SSI and MSI. Next, MOS technology. MOS technology can be used to design large scale integrated circuits and very large scale integrated circuits. In MOS technology, again, three techniques are there. One is PMOS technology, NMOS technology, CMOS technology. PMOS technology means the circuit is designed by using only PMOS transistors. NMOS technology means IC is designed by using only NMOS transistors. Where CMOS technology, CMOS stands for complementary metal oxide semiconductor. Nothing but it is consisting of both NMOS and PMOS transistors. So it is having both the advantages of NMOS transistors and PMOS transistors. That's why CMOS technology is more preferred compared to NMOS and PMOS transistors. If you compare only NMOS and PMOS, NMOS technology is preferred. Why? Because the mobility of electrons is high compared to mobility of holes. Then we will see what are the transistors, types of transistors. We have bipolar junction transistors, in which again categorized into NPN and PNP transistors, and field effect transistors. So field effect transistors are voltage controlled devices. That is nothing but by controlling the input voltage we can able to control the output current. These field effect transistors are again categorized into two types: junction field effect transistor or JFETs and metal oxide semiconductor field effect transistors or MOSFETs. Again, by depending upon majority charge carriers, JFETs or MOSFETs categorized into N channel and P channel. Okay, N channel JFET, P channel JFET, N channel MOSFET, P channel MOSFET. Again, these MOSFETs classified as depletion mode MOSFETs and enhancement mode MOSFETs. So what is depletion mode MOSFET and enhancement mode MOSFET? What is the difference? In enhancement mode MOSFET, there is no channel existing initially. You have to develop or enhance the channel by applying gate voltage. Whereas in depletion mode MOSFET, the channel is already developed, established. At the time of manufacturing, they will add some impurities and develop the channel. So there is a dedicated channel existing in the MOSFET. Those type of MOSFETs are called as depletion mode MOSFETs. So if you compare CMOS and bipolar technologies, so these are the comparisons given. So the static power dissipation is low in CMOS. The input impedance is high, noise margin is high, packing density is high. We can incorporate more number of MOSFETs in a small area compared to bipolar. Why? Because the MOSFET transistors are smaller in size compared to bipolar, and the power consumption is very small compared to bipolar. Why? Because they are smaller in size compared to bipolar transistors. Fan out is low. They are bidirectional devices. In MOSFETs you can able to interchange source and drain terminals. Next, you should know important definition: feature size. What is feature size? What is the importance of feature size? The feature size is also known as IC technology or technology in VLSI. So if you take MOSFET, it is consisting of source, drain and gate terminals. Between source and drain, gate terminal will be there, and gate region separating these source and drain regions. The space between drain and source is called as a channel. This channel is having a length capital L, and it is having a width that is called as channel width W. This channel length itself, it is known as feature size. That is, whenever the feature size is reduces, automatically the transistor size also reduces, hence we can able to incorporate more number of transistors in the same area. So this channel length itself, it is known as feature size or IC technology. Nowadays the feature size is reduced to 7 nanometers, and this is the side view of MOSFET transistor. It is NMOS transistor. Why? Because in NMOS transistor structure, the substrate is P type and diffusions are N types. If diffusions are N types, then you can easily identify it is as NMOS transistor, and diffusions are P type, then it is PMOS transistor. So here the definition of feature size is given as: the feature size of any semiconductor technology is defined as the minimum length of the MOS transistor channel between the drain and the source. Here it is given the channel length is going on decreasing. Okay, so 180 nano, 130 nano, 90 nano, so like that it is now 7 nanometers is running, and the work is going on a 5 nanometer technology. If you take simple NMOS transistor structure, it looks like this. So in NMOS transistor, here it is substrate. This is substrate. The substrate is of P type substrate you have to take. Then after you have to develop the gate terminal. This gate terminal is developed by incorporating silicon dioxide layer by using oxidation process, then by implanting polysilicon layer. So this gate is also named as polysilicon gate. This silicon dioxide, SiO2, this silicon dioxide is acting as an insulator between this gate terminal and this substrate. Here two diffusions, N-type diffusions are there. One terminal is source, okay, one region is source, another N diffusion region is drain. The electrons can flow from either source to drain or drain to source through the channel. So this space between this region source and drain is called as channel. This channel is having length, channel length capital L. So if you observe this structure, there is no channel existing initially. That's why we can say this structure belongs to enhancement mode NMOS transistor. And here this silicon dioxide is acting as an insulator separating gate and substrate, and the silicon dioxide is acting as an insulator, hence we can call this MOSFETs as insulated gate MOSFET, IG MOSFET. Okay, insulated gate MOSFET transistors. So next we are going to fabrication of MOS transistors. So how these MOSFETs are fabricated? What are the steps involved in the fabrication of MOS transistors? So these are the important steps. If you want to manufacture any IC or a single transistor, you should follow these steps: crystal growth, oxidation, photolithography, etching, diffusion, implantation, metallization and interconnects, encapsulation or packaging. So crystal growth, what is meant by crystal growth? So any semiconductor device is fabricated from silicon. So silicon from where we can get? From sand. So if you purify sand by heating up to some thousands of degrees Celsius, we can melt it by using a technique called as Joukowsky technique. So after that we can able to get the pure silicon ingot. After that you have to add required impurities, then you can able to get this crystal. Oxidation is the process of sending oxygen gas, then it forms the oxide layer. So now we will see crystal growth. So as I said, for crystal growth we are using a method, a technique, Joukowsky technique. The Joukowsky technique uses an apparatus known as crystal puller as shown in figure. We will see in figure like this. So this is the arrangement of Joukowsky technique. So in this there is a chamber. In this chamber we have to melt this silicon by heating up to some thousands of degrees Celsius. The silicon is melting. After that, by using a crystal puller, you have to pull this melted silicon by rotating this. So then you can able to get pure silicon in the form of a rod. That rod is called as ingot. So you will get silicon ingot. So it looks like this. So this is the silicon ingot. So this is a puller. So while this chamber, okay, it is rotating, then you have to pull by using crystal puller. Then you can able to get this type of pure silicon, or it is called as silicon ingot. After getting this silicon ingot, you have to cut it into pieces with the thickness of millimeter range. Those slices are called as silicon wafers. So here you can able to see the silicon wafers. See, these are all silicon wafers. How you are getting? If you cut this silicon ingot into so many pieces, then you will get these type of wafers. On this wafer, you have to fabricate your IC. So if you see single silicon wafer, so this is a single silicon wafer. On this wafer, you can able to fabricate more number of ICs. So here this each individual box is a IC. So nothing but these are called as dies. These are called as dies. On each die you have to design your circuit. Then you have to pack those dies in a sealed cover like this. So you will get this type of processor. So what is the process? First of all, you have to cut these silicon ingots into silicon wafers. Then you have to implanting different layers. You can able to fabricate the circuit on these dies. Then each die is working as a chip. These dies can be packed in sealed covers by using this type of material like plastic. So like that, so many some metals we can use to pack. So what is the necessity of packing? To protect from outer world like temperature. So next step is thermal oxidation. What is the oxidation? Oxidation is nothing but sending oxygen gas into surface of this silicon wafer. Then it forms a layer which is called as silicon dioxide. Why silicon dioxide layer is developed? Acting as a good insulator between gate and substrate. Why oxidation process is first? Why? Because first of all you have to develop the gate terminal, then after you have to develop the source and drain regions. So there are two different types of oxidation methods are there: dry oxidation and wet oxidation. So for dry oxidation, this is the chemical reaction, and for wet oxidation, it is the chemical reaction. For dry oxidation, oxygen is passed through the tube where it reacts with the silicon to form silicon dioxide. Okay, so we are developing the silicon dioxide layer by using oxidation process. Masking and lithography process. So what is the necessity of masking and lithography process? So these can be used to define in which regions you have to develop the source and drain regions. Okay, and this masking and lithography process can be used to define those areas at which you want to implant different layers like metal. So for that purpose we are using masking and lithography process or photolithography process. This is the important step, and these masking and lithography process will be repeated many number of times in the fabrication of an IC. So mask, what is the function of mask here? That mask is having some pattern. According to your design you have to define the mask. Then after, by putting this mask on the silicon wafer, you have to send UV rays by using lens. Then wherever light falls, that area becomes hardened and remaining area will be softened. Now remove those softened areas material which is unwanted by using hydrofluoric acids, then printed pattern on the silicon wafer. Okay, so that is the photolithography process and masking. So mask, photomask. A photomask is used to just like the negative in photography that captures a specific image for later reproduction. So as we know that in olden days we are using photography for that purpose. We are using negative film. Okay, on that film it is having some image, some pattern. By using those pattern they can print the photos. So similarly here also I want some particular design, then it will be printed on the Photomask, then you can able to send the UV rays. Okay, so now we will see arrangement of the photolithography process. This is the silicon wafer. On the silicon wafer I want to develop a pattern. So how to develop a pattern? By using a mask. This is the mask, it is having some pattern. Here you are using lens. Through lens you have to send UV rays. Okay, you have to send UV rays through this lens. It can passes through the mask. According to your pattern, you have to darken some portions on the mask and you have to open some portions on the mask. Then those UV rays will be directly incident on the silicon wafer. Wherever light falls, that area becomes hardened and remaining area or remaining portion will be softened. So like let us assume this is an example. So I want to print this a pattern F on this silicon. So this mask you have to use here. Then you have to send UV rays. According to your pattern, the light will be incident on this silicon wafer. After that you have to remove unwanted layer by using hydrofluoric acid. Okay, whenever you dip this wafer in hydrofluoric acid, those areas at which no incident of the light, those material can be removed, you will get this type of structure. So this is the photolithography process. So etching. So etching is nothing but process of removal of unwanted material on the surface. There are different types of etching processes are there. Wet etching, dry etching, plasma etching, sputter etching. So etching is nothing but simply removing unwanted materials or layers from the silicon wafer or from the surface of the silicon wafer. Diffusion is nothing but ions can pass from high concentration area to low concentration area. So what is the use of diffusion here? Once you have developed the gate terminal, you have to diffuse impurities in two regions to form the source and drain regions. If it is NMOS type, then you have to send N-type impurities. If you want to develop PMOS transistor, you have to diffuse P-type impurities into the surface. In order to achieve selective doping, the technique most commonly used in silicon processing is called as diffusion. The basic principle underlying this process is that the dopant atoms migrate from a region of high concentration to the region of low concentration. That is nothing but diffusion process. So in this diffusion, again you have to use mask. Okay, you have to use mask. Then you have to define those areas in which portion you have to diffuse these impurities should be covered or darkened and remaining portion will be uncovered. Then you have to send UV rays wherever the diffusion requires on those areas, no light will be incident, hence through those regions you can able to diffuse the N-type or P-type impurities. So ion implantation. Ion implantation is an alternative technique for selective doping of the semiconductors. Here we are diffusing the atoms or impurities. In ion implantation, we are heating this silicon wafer up to some degrees Celsius, then we are sending the ions or we are accelerating the ions into that silicon wafer, then they can penetrate into the silicon wafer, hence they can form the N-type region or P-type region according to our requirement. In ion implantation, silicon wafers are placed in a vacuum chamber and the ions are accelerated into the silicon under the influence of electric and magnetic field. The penetration depth depends on the ion energy. So those ions, those impurities can penetrate through the regions. So next, metallization and interconnections. Once diffusion has done, three terminals were developed, that is source and drain through diffusion, and through masking polysilicon layer implanted on silicon dioxide, it forms a gate terminal. So three terminals has been developed, three regions as developed. Now these three terminals should communicate with outer world. How they can communicate? By using terminals. So for that purpose we have to use metallization process. So you have to implant metal on those areas by using again photolithography process. You can able to develop the terminals. Okay, that process is called as metallization. After metallization, it forms the three terminals. Okay, in metallization we are using normally aluminum. Why? Because it is a good conductor which is having low resistivity. Once these three terminals has been developed, then you have to pack that die into a secured chamber. A package is the housing of semiconductor chip. It protects and preserves the performance of the semiconductor devices. Once the die has been developed, you have to pack it properly or you have to seal it properly. Otherwise, cannot work properly. If any small particle fell down, then it can malfunctions. That's why you have to protect that die from dust, from temperature, okay, from other environmental problems. So for that purpose you have to seal it. So we are using this type of materials, plastic, ceramic, laminate, like that. We are using some metals to make seal it, okay, to get packing, to protect from the electrical and mechanical effects. You have to pack it properly.
The first stage in the microchip manufacturing process is called material preparation. In this stage, ordinary quartz sand is converted into pure silicon crystals. The silicon crystals are then converted into rods or ingots at extremely high temperatures. The second stage in the manufacturing process is called wafer fabrication. In this stage, the ingots are sliced into thin discs with great accuracy. Each disc is only a few millimeters in thickness and is called a wafer. Each wafer will eventually grow into hundreds of integrated circuits. The first step in the fabrication process is called chemical vapor deposition. In this step, a thin layer of very pure silicon is deposited on the wafer. This pure silicon will form the base on which the transistors will be grown. The second step in the fabrication process is called thermal oxidation. In this step, the pure silicon is oxidized at very high temperatures to form a thin layer of silicon dioxide, which is nothing but the gate oxide layer of the transistor. The third and final step in the fabrication process is called lithography and is the most important step in the fabrication process. This process involves a series of fully automated steps where wafers are first deposited with a light-sensitive photoresist material. These wafers are then exposed to specific light patterns which are defined by the GDS format, which is the result of the integrated circuit's back-end development flow. The regions exposed to the photoresist are then removed using acids in a process called etching. The unexposed regions protect the lower layers from reacting to material deposition, thereby forming specific patterns. The process of photoresist application, lighting, etching, and material deposition is repeated several times until several millions of transistors are created and connected, forming several hundreds of chips on one wafer. The next stage in microchip manufacture is testing and assembly. The first step involves testing each chip in the wafer for manufacturing defects. This helps in early identification and elimination of defective parts before assembly, thereby reducing assembly cost. The wafer is then sliced into multiple chips and sent to the packaging unit. Each integrated circuit is placed in protective bases, bonded and packaged based on the packaging requirement.